For the circuit of figure 2, sketch the wave shape that you would expect to observe if VI was a triangular wave shape with a peak value of 10 volts, i.e. a positive peak of 10 volts and a negative peak of minus 10 volts, and the diode had a forward voltage drop of 0.7 volts. What is the largest value of forward current through the diode? So the circuit is like this. And the VO is across there. So our input voltage, or we can draw a graph because this tutorial sheet mostly involves, this problem sheet mostly involves graphs. We'll have a graph of voltage VR and VI against time, and we'll have to have some input voltage, and the input voltage I'll do in blue. This will be time. And then we'll need to know about the output voltage as well. And we can label a few things here too. We can say that nearly. Wow. This is minus 10 volts, and this is plus 10 volts, and we'll do VR in a different colour. We'll do it in green. So V in is blue and V out is green, but we still don't really know what V out looks like, so we'll have to have a little look at the circuit. So to make the diode on the point of conduction, we'll have to have 0.7 volts across there, and we'll have no current flowing through it. So the question that we have to ask ourselves is, what does VI have to be to make this true? Well, we can add up perform Kirchhoff on this loop here, Kirchhoff's voltage law, and we can say, as usual, if there's no current in this branch and there's only one loop, then there's no current in that, or that, or that, or that. And since this is a resistor, we know that if there's no current here, there can't be any voltage across the resistor. So that's 0 volts. And if that's the case, then we've got 4.3 volts here across due to the source, and 0.7 volts across the diode. So across these two, from there to the reference, we'll have to have 5 volts. So this needs to be a plus 5 volts. And there's no voltage there, so this will have to be a plus 5 volts as well. So when VI is 5 volts, the diode is on the point of conduction. Okay, well, we know where VI is 5 volts is on the graph. It's here, it's halfway between 0 and 10. So something is going to happen here. This is the line on the point of conduction. And in this space here, we have diode conducting, and in this space here, we have diode not conducting. So we can draw our output voltage now, more or less, because we can say, well look, if the diode is conducting, it'll have 0.7 volts across it, and it will never have more than 0.7 volts across it if it's conducting, irrespective of the amount of current it conducts. Once it's conducting, 0.7 volts is across it. Same goes for this source. It's a 4.3 volt source, and it doesn't matter how much current you put in or take out of it, 0.3 is what's across it. So while the diode is conducting, there is no other option but for there to be 5 volts across the diode and the source. So while in the region of conduction, we know our output must look like that. And while the diode is not conducting, so Vi is less than 5 volts, all this stuff here, if it's not conducting, there's no current through. And if there's no current through the diode, there's no current through the resistor either, because there's only one loop. And if there's no current through this resistor, whatever voltage we've got here on this side of the resistor must be the voltage that we end up with here on this side of the resistor. So for all the values of Vi where there is no conductor, all this stuff here, V out must follow Vi, because there's no current flowing through R to drop a voltage. So we should have something like this. Wow, that's bad. So that's what our VR looks like. So the other part of the question asks about current. What is the largest value of full current through the diode? Okay, well, the diode is going to have current in this region here and in this region here when it's conducting. So what we're really interested in is the maximum voltage drop across R, because that's the thing that determines the current in the diode. We've got the biggest voltage drop across R and have the biggest current through R. And since the current that flows through R is also the current that flows through D, it's the resistor that will be setting the maximum current. And the biggest voltage across the resistor is going to be at this peak between there and there. And this is 5 and that's 10 volts. So we will end up with 5 volts across R, given the value of R, are we? We are, it's a kiloohm. Ah, who'd have thunk it? R is a kiloohm. So I can call it 1k ohm. Oh, that makes, sorry. That's really unclear. Try again. So R is a kiloohm, so we can work out exactly what the current's going to be, because we know we've got 5 volts across it, so we'll just do Ohm's law. I is V over R, 5 over 1k is 5 milliamps. So we can, if you wanted to, the question doesn't ask for it, but if you wanted to, you could draw a graph of the current, and what you'd have is nothing, 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 and at this point you'd have current flow, and the current flow would build up to the point where it was a maximum, about here, and then it would decay away again to nothing, and then so your current would follow your voltage. So that's the maximum current is 5 milliamps, and it occurs just there and just there. And if we carry on, there'll be another one over here if we drew the graph some more. Alrighty. So the key thing here is to decide the current that's flowing in the diode. We're worried about what happens to the resistor. You might be tempted at this point to go, oh, I need the current in the diode, I'll apply the diode equation. That won't help. Because we're saying that the diode conducting state voltage is 0.7. So the diode equation isn't going to be of any use there, because we're not thinking about the diode as if it obeys the diode equation. We're thinking about it as something which is either off or on. And when it's on, it's got 0.7 volts across it, and when it's off, it's got less. Or when it's off, it's got no current and less than 0.7 voltage. 0.7 volts. So it's the the circuit elements that surround the diode, which determine the currents that are involved, not in fact the diode itself.